Welcome to the 26th class meeting of the Introduction to DSP. We will have the homework. There will be many MATLAB problems related to what you've seen in the recent class meetings. About the voluntary project, there are only a few students who volunteered to do the project. I encourage you to participate more students to do the project. Okay, here goes the outline. So we've done this part in the last class meeting and started to study the chapter 10 of the textbook related to the applications of the DFT. So last time we've seen, where it is, this figure. And this is the kind of the most important figure in chapter 10. So please have it in your brain so that you are not confused any longer. So it's all about the continuous time signal, uniform sampling, and use of DFT to find out or extract some information about the original continuous time signal. So here is the signal, S sub C of t. Here, subscript C probably means continuous time. And it is not directly uniformly sampled, but first, a low-pass filter is used to avoid or reduce the effect of aliasing. Such a filter is called anti-alias filter or anti-aliasing filter. And in most of the literatures, such a filter is abbreviated to AAF, anti-aliasing filter. Ready? And this filtered signal still continuous. So X subscript C is then CT to DT converted by a uniform sampler. Here, the sampler is assumed to have sampling frequency f sub s. Usually we use the f sub s, where subscript s means sampling rate. But as you've seen already, our textbooks somehow avoided to use this f sub s notation in this chapter, and also only use capital T instead of capital T sub s, but I really prefer these notations. So even though you may be a little bit confused by my use of T sub s and the author's use of capital T, but please just understand they mean the same. So here goes the discrete time signal, and here x of n is defined as x sub c evaluated at every integer multiple of t sub s, or simply capital T. And here goes a multiplier that multiplies this continuous time signal with the w sub n. Here, this is so-called a window function, or sometimes people call it a windowing function. But the textbook just keep using window function or a window. By the way, this window function could be a rectangular window or other Han window, or some people say Hanning window, and Hamming window. By the way, it was very confusing when I first learned. Han is the last name of the kind of inventor. Hamming is the last name of the inventor. So it's Hanning window, Hamming window. It may not be precise. Han window and Hamming window. Anyway, and there should be a lot of other possible window functions. So depending on your choice of window function, your output may vary. So please keep in mind, this choice is all up to you. And unfortunately, which window is proper for your specific use really depends on your specific use. So there is no rule to choose one of the window over the other. And you will see why that. But most of the windows listed here, all of them actually are time limited. Or even though the descripting function is not time limited, but usually this window function itself is a function or a sequence multiplied by a rectangular pulse. So it's time limited. Got it? And our convention for window function is that it starts from 0. And let me correct. I found the authors love not n-1, but l-1. So this L means length of the window or window function. Got it? And this length L signal with a lot of zeros now goes in. And here, if we choose N DFT, means we cut from 0 up to n-1 of this signal V, and then perform N point DFT. Of course, N could be smaller than L, larger than L, but we usually consider two cases only, N equals L or N greater than L. In that case, since only L of the terms can be non-zero, it's similar to we append 0 vector to the length L vector to make the overall vector of length N. So in this case, we assume 0 padding. Got it? So I hope you remember the details. So window function has length L, and DFT has N points. And if N greater than L, we assume 0 padding. Got it? And last time, I emphasized one of the most important thing you need to remember. So suppose your continuous time signal to be sampled has CTFT, capital X sub C of j omega, that roughly ranges. Here, the reason why I say roughly means that the anti-aliasing filter may not be strictly band limited. It may introduce a little bit of aliasing, but anyway, so here goes the sampling frequency. And with that sampling frequency, when you multiply sampling function, you remember what is the sampling function. It's a kind of fictitious signal consisting of delta functions equally spaced with capital T sub s in this case, right? And if you multiply this sampling function to x sub c, what happens? The output signal has folded spectrum with folding period equal to 2 pi over capital T when it is in radians per second, or 1 over T when the frequency is in hertz. So you have some spectrum that is repeated with period f sub s. So when it is converted to the DTFT, then what happens? You must remember that in radian frequency, pi means sampling frequency divided by 2 hertz. Got it? You must always remember. So this relation, pi corresponds to half the sampling rate in hertz, is not determined by your choice of L. Choice of L not depends on your choice of N, but your choice of sampling frequency. Got it? So today you will see many figures with slightly different choice in the parameters. But if they have the same sampling frequency, then from your original continuous time signal to the discrete time signal or vector to be transformed, they all satisfy that relation. Only the sampling rate determines in DTFT, the pi corresponds to half the sampling rate. Got it? So that was the thing what is emphasized in the last part of the last class meeting. So let's see one of the examples. Got it? So here is the CTFT of a continuous time signal, S sub C. By the way, our textbook use capital omega and lowercase omega to denote radians per second, the angular frequency. This is for continuous time signal, that for a discrete time signal. So you may say that it's confusing, but anyway. So here, this is CTFT. It may be non-band limited signal. And the author just wanted to talk about that. It could be possibly not band limited. Okay? And now we have the anti-aliasing filter. And this anti-aliasing filter itself does not introduce aliasing. So the author just assumed that around, what is this one? This is 2 pi to t. So got it? So this is the this corresponds to half the sampling rate, and your anti-aliasing filter anyway dies out before it reaches this half the sampling rate. It is not necessary to have that shape. Maybe such a shape in ideal case or something like this. But anyway, here goes an example. Now, this signal is LTI filtered with the low-pass filter with impulse frequency response like this. So by the convolution theorem, you have the input signal CTFT to the CT to DT converter. So still continuous time signal you have. And this one multiplied that one is shown here. So far so good. So let me show you again. So this is what that band unlimited signal. And this is what? This is what? This is the anti-aliasing filter. And that has what? This one. So since we have label ABC, so this corresponds to A, that B, and this one is C. Got it? So the next question would be that one. And as I told you, from here to that, what do we have? Spectrum folding and scaling in the x-axis, so that, of course, y-axis too, but so that we have half the sampling rate corresponds to plus pi. So here you have plus pi. That corresponds to what? Pi over t radians per sec, which is what? 2 pi times half the sampling rate, radians per sec. So half the sampling rate in hertz. Got it? And of course, you have this repetition for spectrum folding. So here we are now up to this point D. Got it? Now you do what? You multiply a window function. Be careful, up to here to here is a linear operation. And especially this is an LTI filter, so this is LTI filtering. Let me ask you a question. What about this one? Is this a linear system? CT to DT converter is a linear system? Yes. Is it linear time invariant? No, right? Be careful. Inside this one, you have a multiplier that multiplies periodic impulse train to the input signal, right? So if you delay the signal, then this signal is not just delayed. It's sampled in slightly offsetted sampling instance, and unless the signal is constant or very special, you don't have time invariance. So this is a linear system. Now, from here to here, is it a linear system? Yes, still linear, but again, this is fixed. So if you delay that one, you don't have the delayed version because this is fixed. If this is also shifted, you may have the same signal exactly, right? But anyway, so be careful. LTI, linear, linear. But we still know from the duality of the analysis and synthesis equations, we know that the output is what? Output is the circular convolution. The output DTFT is the circular convolution between the DTFT of that one and DTFT of that one. So now my question is, what do we need to analyze first? The DTFT of our window functions, right? So let's see the DTFT of our window functions, especially first the rectangular window. And the rectangular window has DTFT, looks like this. Of course, this is the magnitude of the DTFT. And it looks very familiar. You've seen this in the homework problem. Some students have seen it again in this year's QE, Math A. What is it? It is related to so-called the Dirichlet kernel. And as you remember, this signal is related to the Dirichlet kernel with proper choice of number of terms. And this signal is periodic. And you may say, that, where is the period? In this case, period is 2 pi. The period depends on how you define the Dirichlet kernel. So it's kind of repeating impulse signal, but anyway, it's not precisely impulse. It's like more like a sync pulse in continuous time signal. The difference is that this one is something like sine over sine, not sine x over x. That is continuous time sync. Since the numerator is periodic, denominator is periodic, and their periods are harmonically related, the signal is periodic. That's the difference between the Dirichlet kernel and the sync pulse. Sync pulse is not periodic because it's sine pi x divided by pi x. The numerator is periodic, denominator is not. But the Dirichlet kernel is periodic. Now, we know that the only parameter for us to choose is what? The length of or duration of this rectangular pulse, right? We assume that the window function possibly has non-zero values from 0 to L minus 1, right? So since this is the DTFT of the signal, no vectorization by cutting out all the zeros. All ones starts from 0, ends at L minus 1. Now, if we change L, the value L, what would change here? Zero crossing rate. Actually, even though this is the all non-negative because we have taken the absolute value, looks similar to sync pulse if it is well centered so that W can be real, but in this case it cannot be real. But anyway, it's related to sine over sine, so it goes down by crossing 0, goes up crossing 0, down, up, down, up, down, up, down, up, and actually it amplifies again to peak and goes down. So if you increase L, what will happen? More and more zero crossings between these two pi intervals. Got it? So remember that qualitative property of the Dirichlet kernel. Now, what about other window functions? So I said that the rectangular window could be chosen. Han, or some people say Henning window can be chosen. Hamming window, Kaiser, Blankman, some other many important window functions. Our textbook shows 3 of them. No, just 2 with different parameters. Okay. It seems that the slide does not have it. Okay, so let me show you the Kaiser window. And the Kaiser window is defined like this. Very strange at the first glance. So this capital K means Kaiser here. So Kaiser window, again, depending on the material you look up, sometimes a function is defined as totally symmetric function. But in our textbook, it always starts from 0 and ends at L minus 1. And the center is really the center of 2 points, 0 and L minus 1. So intentionally, our authors of the textbook has chosen alpha defined as half of 0 plus L minus 1. So that if you plot this one, plot this discrete time signal, it looks like a symmetrical function. It looks as a symmetrical function always. Got it? So it ranges from 0 to L minus 1. And it involves your hated modified Bessel function of the zeroth order. And here goes the parameter beta that determines this window. So actually, without cutting the signal, so that is of finite duration. Suppose you only look at that part and ignores centering, then what will happen? Yeah, but I still remember that you need to have alpha. But anyway, so in this form, you have two parameters, alpha and beta, to choose. But alpha is more like determined fixed as this one. So you have only one parameter given the value of L. Got it? So L is given, your choice is just beta. And beta may be some positive number, and here goes different choices. So when beta equals 0, you can show that the window is just a rectangular window. So even though it says 0 to 20, and maybe L equals 21, right? So this is 21 minus 1. So L equals 21. And as I told you, it looks like a symmetric function. Of course, I really hate the author's use of solid and the dash dot dashed lines, because this is a discrete time signal. So if I were them, probably I have used the discrete time axis with index n and use the stem, so that I really wanted to emphasize it's a discrete time signal yet. Got it? So W of n is a discrete time signal that is kind of sampled version of this one. And it includes the rectangular pulse as a special case with beta equals 0. And if you choose larger and larger value, it has a tendency to suppress the edges of this rectangular window more and more. Got it? And now, as I told you, the W of e to the j omega is very important. So by using handcrafted DTFT, you have this one. Since the W of n is real valued and the spectrum is symmetrical, so they have used I remember 20 log 10 base, the magnitude response. And you see here, as shown here, the solid dash dot and dashed lines have beta increasing. And you see that this solid has beta 0. Of course, this is actually touches 0, but since this is log, there is no 0, negative infinity. And by increasing the value beta, and you remember we suppress the edge parts more and more, you have what? You have larger and larger, so-called the main lobe. By the way, these are called lobes. And the first part is called main lobe. And the others are called side lobes. Got it? It's like in Korean, 그 치마들 중에서 왜 이렇게 옛날 치마들 보면 이렇게 울렁울렁하게 이렇게 돼 있는 거 있잖아요. 그러면은 그게 하나하나가 로브인 거예요. 알겠죠? 네. Okay. So as you see in the frequency domain, the increasing beta makes the width of main lobe larger and larger. In that sense, it's not good, because we are going to circularly convolve the DTFT of the window function with the incoming DT signal. So unless this has in the frequency domain delta function, you have kind of blurring effect. of the inputs DTFT because you have to convolve, right? So we want to have that main lobe width smaller. However, unfortunately, given the time limitation of the window functions, if you decrease the width of main lobe, you have increased level of side lobes, which means that in the frequency domain, you have very sharp main lobe, but the side lobes are larger. Got it? If you have bigger main lobe, then side lobes quickly dies out. So we have a trade-off. That's why, as I told you, even given the family of the Kaiser window, you don't know which parameter set to choose. It depends on your application. Sometimes people just tries many different choices of parameters and choose that shows the best result. So it's a trick. It's not at the level of academic dishonesty, but usually people do that. So that's the trouble so far. You may use some AI machine learning model to optimize the parameter, depending on your output. Anyway, so let's consider windowing of some signal and see the example, what I mean. So next section, just do this one, shown in section 10.1, by choosing specific input signal. And you must be alert and follow my explanation carefully. So again, so this is A, where is B? Yeah, so there is no B. C. Yeah. C part is X of N, right? D part, D. Okay. So this corresponds to D, and window is E, and this is F. Got it? So you have original continuous time signal consisting of two sinusoidal signals, all real valued. And their radiant frequencies are different. The first term has capital omega 1, second one has omega 0 and omega 1, and phase doesn't matter much. But anyway, so we have this case. And now this is uniformly sampled to generate this signal. So we are not kind of having any anti-aliasing filter because this is already band limited. But in order to have no aliasing, we choose the sampling rate greater than twice of these values. And for the first example, what we do is that we, for example, choose capital T equals 10 to the minus 4 second. That is what? 0.1 millisecond. Okay. And choose the radiant frequencies as this one. So after we convert to the discrete time signal, we have omega 0, 2 pi over 6, and omega 1, 2 pi over 3. Got it? So suppose you plot the DTFT of x, then what do you guess? You have Dirac delta functions. Of course, depending on this phase, you may have some phase shifting constant multiplied to these Dirac delta functions. Got it? Now, this is what? This is a periodic signal if our choice is used. And it's not an energy signal, it's a power signal. So precisely speaking, we have delta functions. That is the generalized version of the Fourier transform, Fourier planetary transform. But anyway, we use window function. Now, suppose we have used the, is it rectangular? Yeah, rectangular window or some general window function. Then what happens? This W of n multiplied by cosine function when it is Fourier transformed becomes what? The window functions DTFT shifted by the frequencies. So you have these shifted versions of the DTFT of the window function appearing 4 times with proper shift. So if this is the spectrum of Fourier transform of the window function, then you will see that is appearing 4 times like this. Now, see this sky blue line, and you will see that the delta function is now blurred to, in this case, Dirichlet kernel or something. So here goes my question. Do you want a larger main lobe or smaller main lobe in this case if you want to take a look at the output and find out the value of the frequencies? You may have smaller, right? However, as I told you, you have not only the main lobe, but the side lobes. And due to the high side lobes, larger side lobes with smaller main lobe width, we have dilemma. So let's see the dilemma. Now suppose we have chosen different frequencies closer to each other. And you may say that it's okay still. So suppose we have the rectangular pulse with smallest main lobe, and it seems that this peak, that peak, that peak, that peak, hey, I can find the original frequencies of the continuous time signal. Is it really true? The authors challenges you, and they choose more and more close pairs. And now let's see what happens. Now, the 2 of the shifted window functions DTFTs overlap a lot. So main lobe of the one DTFT, one DTFT and side lobe, another DTFT is now interferes like this. Now let me ask you a question. Suppose you didn't know the original signal consists of 2 cosine functions. Without knowing that, from here, can you say how many cosine functions exist originally in the continuous time signal? And what are the carrier frequencies of them? And you still may say that, hey, this one, that one. But actually, by picking up the local max values and finding the locations, actually, you start to have errors. And now, here goes a more challenging case. Now, they are very, very close. And what happens here? Most of you say that without knowing two signals existed, say that maybe just one signal with some possibly corrupting some interference or noise. Ready? So we have a dilemma. We want to have smaller width of the main lobe, but we also want to have lower side lobe. And that cannot be satisfied at the same time. Some of you may confront this dilemma again and again because these days, as I told you in the last class meeting, at the end of last class meeting, communications and sensing, especially radio wave-based sensing, is radar kind of, right? So radar and communication is more and more combined, and that is the future, what our communication engineers imagine. You will see what troubled radar engineers for around 100 years. You will confront that problems again. In radar engineering, what do you want to do? You want to resolve how many targets are there, for example, on the sky, in the sky. And what are the Doppler frequency shifts, so that you want to know not only the number of targets, but also the radial velocity of each target. The situation is very similar to this problem with tone signals. The different tones means what? In this case, the different frequencies may correspond to the different angle of arrival, possibly, if we have the kind of duality. And this peak may be related to the target's cross-section, size of the cross-section. And you want to resolve these targets. The problem is that sometimes you sacrifice the accuracy in your speed. So they introduced a lot of different kinds of window functions too. And so-called side lobe suppression is one of the most important old signal processing problems in radar signal processing. So they developed some interesting filters, like here is the main lobe, and side lobes have almost the same amplitude. And as you see here, there it is. When you have a Kaiser window, right? Since this is more rectangular, you have around 20 dB per decade type thing. And here it's kind of slightly decreasing. But some filter really has some main lobe and of course side lobes, but their peaks are almost the same. And you may say that, hey, still the side lobes have the same height. But in radio sensing or communications, we have so-called what? The noise floor. And noise, we assume, are white. And as far as that level of side lobes are not that great to make our estimation of some parameter troubled, then anyway, we have noise and the effect is almost the same. We don't want to be misled by the large side lobes. Got it? Anyway, so now you understand the importance of the width of main lobe and importance of the height of the side lobe in resolving some signals when we really do practical signal processing. Here, practical signal processing means what? This type of signal processing. And this is really true because we rarely perform DTFT. We usually perform DFT. even though it looks like DTFT, actually we do DFT because what? As you see here, we usually cut out some countably infinite terms in the signal and just see a segment, which is a vectorized version of a signal. And if we perform DTFT, it's like DFT, right? Got it? And when you cut, if you do not properly adjust the amplitude with some window, it's same as you use a rectangular window. That is not good. Got it? So there has been many claims that this window is better in, for example, human acoustics, human voice signal processing. That is better in some acoustic signal processing, blah, 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 blah. And by the way, once the Professor Gallagher, who invented LDPC code, he provided the so-called open courseware with the video lectures on their MIT OCW. I watched one of the lectures and he was talking about his colleagues at his young ages. And his friends who are as smart as him joined a lot of industrial research institutes. Unfortunately, he implied that most of them were wasted. He didn't say wasted, but kind of wasted their intelligence trying to find out proper choice of parameter in the window function. But anyway, the choice really becomes patterns. Like this choice of parameter in the encoder, some signal processing interpolation of voice works well, far exceeding other choices of vectors in human evaluation, blah, blah, blah. And that makes a good pattern application. And AT&T Bell Labs has a lot of smart researchers wasted their intelligence finding out or tuning those parameters. But we really appreciate their efforts these days, actually. We do not notice, but for example, if you play any, for example, such apps like Windows Media Player or GOM Player or something, probably you've seen so-called codecs. And codecs has a lot of algorithms to do signal processing. And each block has now probably expired patents that obtained by exchanging the life of young engineer. Anyway, so let me continue. So what do we do? So here we have the CT to DT conversion in frequency domain. So we have the spectrum folding. And what happens? Suppose this is the DTFT of the window function viewed as a discrete time signal. Then from our knowledge learned in signal and systems and in this course, what do? We circular convolve this signal with that signal. And since this lobe has some width, non-zero width, it's not direct delta functions consist. What happens when you convolve them? These blurs spreads each points and add them up to have such a smoother, in good sense, smoother curve, but kind of distorted function. So this is what? This is A, B, C, D, E, 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 E. Yeah, this one. E, right? Now here goes F part. By the way, this line is the F part. And then what are these lines? When we evaluate this function of continuous parameter omega, and suppose we use the MATLAB stem function, then our plot will look more similar without having these interpolating lines, right? Got it? Do you understand what I mean? So it's a kind of overlap between the original DTFT and evaluated version. But why the authors have this one? Because we have NDFT. So number of points now in DFT determines what? Determines how many points do you have within this 2 pi period to evaluate your output DTFT. So DFT allows us to evaluate DTFT, but not all values of omega, but specific integer multiple of 2 pi over the number of points. So here, this spacing is determined by the choice of points in DFT. Got it? So suppose we have fixed rectangular window with length L. Then the L determines what? How much the folded spectrum blurred. If L is large, then our Dirichlet kernel has very small width of the main lobe, so blurring is a little bit suppressed, right? But anyway, when you finally evaluate, this number of points determines everything. But this number may be large, equal to L, of course smaller than N. In the case we cut out, but we assume that equal or larger. Then the final question is, what's the difference when we increase the value of N over the value of L? So in other words, what if we pad more and more zeros before we perform DFT? So suppose we have cut out L of our samples. Now to make it a length N vector, we pad zeros. If we increase N more, then more and more or longer and longer zeros must be padded. What will happen? What will happen where? That is also. See that? So far, right, up to this point, if L is fixed, zero padding means nothing at this point, right? Zero padding means we are going to remove the countably infinite terms from this V of N. So choice of L or number of points does not change the DTFT of the signal to be evaluated. Then what? That is shown here. Let me move up to here. So here, the length of the, in this case, Kaiser window with beta equals 6, I remember, yeah, is given. And now we choose not to pad any zero here. We choose same number of zeros as, so 32. In this case, 96. Then, as you see that, suppose we have the original envelope of the DTFT. Then the DFT output more densely evaluates the DTFT. That's all. Got it? Given the same length of vector, but you pad more zeros, what will happen? of course, you have a longer and longer output, and that longer and longer output must be kind of squeezed to 0 to 2 pi if you really want to plot DTFT. And if you really want to plot estimate of CTFT, then you must cut and fold and plot from what? From negative half of the sampling frequency up to half of the sampling frequency, right? So only the resolution is increased. But you may say that, hey, if we already have blurred too much, there were very closely located two delta functions, but window function has very bad side lobes. So the two main lobes and side lobes blurred each other. Then padding 0 does not improve anything. But it's better than have very small ones. Anyway, if we connect these points, so far in MATLAB, it's a kind of stem something. Of course, we can do what? In MATLAB, plot something. Then we have smooth curve, right? By the way, this figure is a little bit misleading because here they talk about linear interpolation, which means the use of plot function instead of stem function in MATLAB. But what is really shown is not related to linear interpolation, but the size of window actually. If the window, suppose you use rectangular window with longer and longer L, which means that you have very small width of the main lobe, enables you to resolve these things. So if you see the parameters, right, the N is fixed and L is increased. Got it? So I emphasized a lot, but there are a few of choices in our parameter setting. The first thing is what? Of course, the sampling rate and related anti-aliasing filters shape. Got it? So sampling rate determines a lot. Then what? Length of the window function, assuming it's of finite duration. Second, how many zeros are to be padded. Each parameter affects our final result. And you may want to use plot instead of stem if you are interested in the kind of estimating or approximate CTFT of the original signal. But careful, be careful that your plot function, the output of plot function, is what? Is a distorted version of the CTFT of the input signal. In what sense? First, see that you have rectangular window or some finite duration window. What does that mean? Your original signal then may have very strange shape before you cut out and after you cut out. These informations are gone. So your DFT output does not reflect any effect outside your window. So you actually distort the signal a lot by cutting out most of the information except within the window length. And then you replace the original signal as a time-limited signal, and then you sample, and then you perform DTFT, and then you sample the DTFT by doing the DFT. Got it? So always remember that this discrete digital signal processing that usually processes a vector loses possibly a lot of information outside your observation window. You must remember this. Otherwise, you will get confused again and again and again. And sometimes will make serious, unrecoverable mistake, especially when you are applying this knowledge in financial signal processing. Got it? Now, since we have 15 minutes and we have a lot to cover, let me briefly browse the rest of the sections. Section 10, by the way, I've skipped some of the, I believe I've done most of them. Okay, got it. So section 10.3 is all related to so-called short-time Fourier transform. Our textbook somehow, I don't know why, does not introduce this very important acronym. By the way, acronym means name. Acronym is a kind of collection of characters taken usually from the first characters of each word, CTFT, short time Fourier transform. This is very, 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 very important in practical signal processing, especially in old acoustic signal processing and speech signal processing. And suppose we don't have that course, but suppose you take speech recognition and processing course, then the first few chapters will introduce you short time Fourier transform. And also, suppose you have purchased a freeware or shareware from the internet, which can process your, for example, wave file to convert it to MP3 file, or you want to scale the signal, so normalize the amplitude, or do some filtering. Then usually they have a lot of important buttons to show the result, show the file in your screen. One is, of course, the plot of the signal. And second one is what? The short time Fourier transform. So let me show you an example first. Where it is? Yeah, I believe this. Yeah. Now, sometimes when I magnify, it just goes to the first of the page. So as you see, this is the time axis, time in second. So 0, 0.1, 2, 3, 4, and 1.0 and 2.0. So this is around 2-second duration. And during 2-second duration, the utterer says in English, 2 plus 7 is less than 10. Got it? And now, in the time domain, what do? Can you kind of, for example, you build a software and you input this sample of length 2 seconds, properly sampled, and so it's a vector. So you punch in the vector, you provide the vector, and probably this would be your desired output, text. This is called voice to text task. Okay, so our job to do is voice to text. And this era of machine learning and artificial intelligence, you may say that, yeah, we have a lot of applications that does perfectly, right? But when I was at your age, this was not simple. Why? Why? Because at my age, I was dumber than you? No. Our human beings were on the race of what? Development. So at that time, people wanted to do that. They wanted to develop some algorithm, but what was the limitation? Not the intelligence, but the computing power. Depending on the available computing power, people develop suitable algorithm. Sometimes algorithms are tested and then proved to be working. Before developing the algorithm and implementing it, sometimes we never know whether it's working or not. And at that time, we were hungry in computing power. There were no very, very fast and very, very inexpensive hardwares. So people worked inside the box. What is the box? The computational limitation. And they started to check one by one. So the first one was that, okay, in the time domain, can we just see and find this means to anybody from this waveform, time domain waveform? Can you see this means 2 and this means plus? Probably not. And people have found that asking two assistants pronouncing the same text, one is male and the other is female, and from the time domain plot, they couldn't distinguish any word, for example. So what did they do? They were educated and they wanted to work in the frequency domain. And this is a vector. Now, given a vector, assuming that that is a part of, for example, this is only discrete time signal, a discrete time signal with infinite duration, the first choice would be DTFT. So by padding zeros, and you may consider DTFT, but you know that anyway, DTFT may not mean much in this case. They wanted to find out these characters. So first thing actually was indeed working in the time domain to find out so-called how to segment, how to divide these vectors into sub-vectors. Because if you compute the magnitude square of each sample, of course here you have some things, but probably here and there you have very small values. Even though the algorithms may not work very good, we know how people pronounce. We cannot speak extremely fast because we have to move our muscles, to move our skeletons and these tissues, which has mass, which means that inertia. So we cannot speak very fast. Even though these days we play twice the speed and all the YouTubers speaks very fast, we understand. So they had the idea of segment. They wanted to segment the signal. The problem was that, as I told you, if we use so-called instantaneous power-based segmentation, it works only when the sound is recorded in a quiet place. For example, inside a restaurant, there were a lot of other guests who makes a lot of noises. Then even though I do not speak anything, our time domain algorithm will automatically, wrongly, segment the signal and give that to the next step. So interestingly, when I was taking the speech signal processing course, the professor says that, hey, we have found out a good length for segmentation, something millisecond. Use it. Got it? Probably this length would have been also found those almost genius minds worked in AT&T Bell Labs in probably 1960s or something. Yeah. They tried to find out the optimal segment, deterministic segment length for normal speed utterers, something like that. Anyway, so that was not good. And so given the signal, they just wanted to have something similar to DTFT, but much better to reflect the instantaneous information. Consider that we know that x of t and x of t minus some tau has what? Has spectrum almost the same when we only see the magnitude over intensity, right? So CTFT and DTFT does not well provide us how the information bearing sequence of, in this case, words are ordered in time. So they wanted to kind of introduce new Fourier transform that not only works in the time domain, but also works, not only works in the frequency domain, but also in the time domain. Then what would be the idea? The simplest idea is what? Use the window function. So here goes the idea. Let me show you the equation because we are more, things well with equations. So here, our new transform, short time Fourier transform, has two parameters. Again, time and frequency. Frequency is here lambda. And what is the input? Input is X sequence. And what is the output? Output is what? Something very strange. Compared to DTFT, we have one more parameter. So again, we still have time parameter. Then what happens inside here? What we do is that, of course, we practically delay the signal and delay the window, but theoretically, we advance the signal in the m-axis. And here is the window function, fixed. For example, 0 to L minus 1. Got it? And we perform the windowed version of, we perform the DTFT. See that this is DTFT? Worked on the windowed version of the input, advanced. So what we do is that we fix this one and that one. And slide the window actually by advancing the signal by n. So here n means the time advance. But you can just say that, okay, what I do is that I take that part and do Fourier analysis. I take that part, Fourier analysis, that part, DTFT, that part, something like that. Because usually after computing this one, this is in general complex value, we take what? 20 log absolute value of this one. So anyway, phase information will be gone. So sliding the window is the same as advancing the signal. So what we have is something like this one. Suppose our input signal is a linear chop signal. By the way, about the chop, I already explained what is chopping, jack. And the simplest chop signal is really has unlimited duration and infinitely increasing frequency. It's not like jack. It's like a up to possible infinity. But anyway, we are going to use a rectangular window. So anyway, so here we fix the window, and from 0, here goes the linear chop. Now we choose 720. What does that mean? We advance the signal. So this signal is advanced. So this higher and higher frequency part is now windowed by this window. And then we perform DTFT. But you may say that, what DTFT? Actually, we do DFT, possibly padding zeros and performing NDFT. Then it's like we evaluate DTFT at endpoints. And we may interpolate the signal. Then we have, this is the original spectrum, DTFT, of the original signal without windowing. And this is what? When n equals 320, at which what? The nominal frequency is around 0.07, right? At n equals 720, we have higher frequency. So if we increase n, actually, in the short time Fourier transform, we have a peak that moves linearly, unlike the CTFT of the original signal or DTFT of the sampled signal. Here, we don't have any time dependence. We don't know, even if we reverse, so it's like frequency is linearly decreasing, we have the same spectrum, magnitude square. But short time Fourier transform gives you the information, which one appears around at what time. So you may have, in this case, 0, some linear chop, tone, 2 tones, and your different choices of lengths gives you short time Fourier transform. This is the index n. See that? Linear chop, single tone, double tones. Got it? So short time Fourier transform is a very good tool to show the frequency contents at each time instant. And you may say that, wait a minute, then why we don't use short time Fourier transform but Fourier transform? Let's talk about that later. Okay, that's all for the day.